We are continuing Module 12. This is the second video. And I have to say before we start this information and this material is probably some of the most interesting or different, or maybe some of you will think strange material in this class. And I don't disagree with that. It seems at first a little crazy, but the good thing is it's not really that hard once you understand the kinds of problems we're working. It's not that hard to be able to understand them and to do them correctly. But it's just a little bit sort of bizarre at first of what we're doing. You can see here, topic is complex numbers. So hopefully all of you can remember being back in algebra and working with complex numbers. Let me just try and give you a very quick review. The whole idea of complex numbers comes on the scene because in math, sometimes you may end up wanting to take, in this case, like the square root of a negative number, which you can't really do, or at least the solution to this is not a real number. However, we can have the answer be a complex number. If you remember, just to make it very clear, it's like if we break this up into -1 times 9, then remember square root of -1, we're now going to call I this imaginary unit. And of course, square root of 9 is just 3. So this ends up being 3i. This is called a complex number. So remember, complex numbers really come about when we're trying to take roots of, especially square roots or fourth roots, even roots of negative numbers. Now, this is a complex number, but when we start working with actual complex numbers, there's two parts, right? For instance, this is a complex number. Remember, this is called the real part, where it's just a normal real number. And this is called the imaginary part, where you have the I. Another example of a complex number, 2 minus 5i. 2 is the real part, -5 is the imaginary part. So sometimes, maybe I'll write it like this. I'll call Z. Z is going to be like just a symbol for my complex number. Z equals 6 plus 3i. So there's a complex number. Now here's where it starts to get interesting, a little different. What they've decided to do in math, instead of just writing this complex number, they decided to try and use a graph and to actually graph complex numbers. What do we mean by that? Well, what they do is, let me write this again. Of course, this is what we call the real part. This is the imaginary part. And what we're going to do is we're going to graph this. And the real part, we're going to graph sort of like what we used to call the x-axis. And the imaginary part, they're going to graph it on what we used to call the y-axis. So in other words, this is going to look like a typical XY graph, but I'm not going to label it X and Y. I'm going to label what we used to call the x-axis, the real axis, and what we used to call the y-axis, I'll call the imaginary axis. So if you were to graph this number, it's almost like we're going to find a point on this graph where the real part is 6 and the imaginary part is 3. And it's just like graphing. So here's 6. Here's 3. So if I want to graph the complex number 6 plus 3i, 6 on the real axis, 3 on the imaginary axis, and that point right there is 6 plus 3i. How about if I try and graph negative 3 plus 2i? Once again, the real part is sort of like my x-axis, and the imaginary part is like my up and down, my y-axis. So minus 3 and then 2. So that point right there, we can say, is the complex number minus 3 plus 2i. In other words, it's almost like, since we know complex number has 2 parts, we make the real part like the horizontal axis and the imaginary part. Now we could have something like, what if that was my complex number? There's no real part, just an imaginary part. How would I graph that? Well, in a sense, the real part's 0, the imaginary part's minus 3, so that point right there would be the complex number negative 3i. So I'm going to call when I try and write a complex number like this and graph it for now, let's call this x plus yi. And for now, I'm going to say when we write the complex number like this, and we graph it like this, I'll call this rectangular coordinates. Because here's what we're going to do now, which is interesting. Let me give you a quick reminder. Now this relates back to polar coordinates. So we've been doing polar coordinates so far. So at first you might think I'm totally headed off in a way different direction. But now you're going to see polar coordinates appear again on the scene. So let's do a quick review. How about I want to plot a good old-fashioned point in rectangular coordinates 2, 4. Right? But we also learned we can graph points with a polar coordinate. So about on the same graph, once again, polar coordinates are r theta. Let's go 3 power over 6. So now we go head off in the power over 6 direction, which is maybe this direction. And now r is like my radius, or the length from the origin. So I'll just make a guesstimate. It's about maybe right here. So that distance is 3. So So therefore we call this point 3 pi over 6 in polar coordinates. And then we learned how to go back and forth. We can take a point in rectangular coordinates and I can rewrite it in polar coordinates, or I can take a point in polar coordinates and rewrite it in rectangular coordinates. So what we're going to do here now, for instance, now with these complex numbers, we're graphing a complex number, the real part and the imaginary part. We could think of this as like a rectangular representation. That's why right here I wrote, if we write a complex number like x plus yi, I'm going to call that writing the complex number with rectangular coordinates. You know what we can do? I can also take that point and I can find this angle and I can find that distance, and I can now represent that point, write it in what I call polar coordinates. So if this is rectangular, pretty straightforward, x and y, how would I write it in polar coordinates? Well, think about this. Remember going back and forth between polar coordinates and rectangular coordinates? You may need to go back and look at your notes, but we had this. If we are given polar coordinates and we're trying to find the x and the y, remember we said x is r times cosine theta, y is r times sine theta. How about for this x and y here, I plug in these polar coordinate little formulas. So now originally this is my z written rectangular, but instead of x, if I replace it with r times cosine of theta, and I replace the y with r times sine theta, I now have expressed or written this complex number in what I call polar coordinates. As a matter of fact, what they normally do is they normally go and factor out the r so they say this is now the equation. This is how we can write a complex number in polar coordinates. So once again, complex number written in rectangular coordinates, which we can graph, but then also we can write a complex number in polar coordinates, and we could also graph it if you wanted to. You've got your angle here, you've got your radius, which is the length from the origin, and you can graph it. So let's just do some quick examples so we can see. For example, let's take a complex number written in rectangular coordinates. Right? 4 plus 2y. I could even go graph that. Four on the real axis, 2 on the imaginary axis, and that right there is. However, let's go ahead and let's take this complex number, and instead of writing it in rectangular coordinates, let's rewrite this in polar coordinates. Now here's where, let me go off to the side and remind you these definitions of going back and forth between polar and rectangular. So remember, rectangular is x and y, polar is r and theta. If you're given rectangular and you're trying to find polar, you've seen these before. Remember, the r is x squared plus y squared, and the theta is the inverse tangent of y over x. Now if we're going the other way, and we're given polar coordinates and trying to find x and y, x equals r cosine theta, y equals r sine theta. All right, we've gone over these now 2 or 3 times. And we're going to use those again here now. Because in a sense, what we're doing is we're going back and forth between rectangular and polar coordinates. So in this case, so I can think of 4 as my x and 2 as my y. I know the polar coordinate is going to look like this. It's going to be r, and then I'm going to have cosine of my angle theta plus I times sine theta. So really, to write this complex number in polar coordinates, I needed to simply figure out r and theta. And once I've got those, then I can write that complex number in polar coordinates. Well, I'm going to use this information over here. If I'm trying to find my r, and I know my x and y, r is the square root of x squared plus y squared. X is 4, so 4 squared, plus y is 2, 2 squared. 16 plus 4, square root of 20. Always got to simplify this. 4 times 5, a 2 comes out. So now I know that r is 2 square root of 5. Now, to get my theta, now this one you always have to be careful of, right? Because inverse trig functions can be tricky. Inverse tangent of y over x, y is 2 and x is 4, or I could say 1/2. And I'm going to grab my calculator. We'll go and do this problem in degrees. Sometimes you may see problems where they give the angle in radians. We'll just do degrees for now. So the inverse tangent of 1/2. Now with these inverse trig functions, you have to be careful. So let's see if this makes sense. 26.6 degrees. Remember, inverse trig functions, the calculator is only going to give you answers over here in the sort of right half of your unit circle. Now, this is where it helps to plot. I'm actually right here, which is in quadrant 1. 26.6 degrees makes sense. That's my actual theta, so I don't have to change it or adjust it. It's good to go. So now I've got my r and my theta, so I can write it as r 2 square root of 5 cosine of 26.6 degrees plus I times sine 26.6 degrees. And if I were to try and graph this, what I'm saying is that angle there is 26.6 degrees. And this distance, which is like r, is 2 square root of 5, which actually has a number. Is like 4.5. Looks reasonable. All right, so what did we do? We started out with the complex number written in rectangular coordinates. I could think of the real part as the x, the imaginary part as the y. Then I was able to rewrite this complex number in polar coordinates, which is right here. Just for fun, let's go ahead, just to give us a little bit of practice, let's go ahead, just to make sure it's clear, let's graph this complex number if it's given to us in polar coordinates. So when you're given a complex number of polar coordinates, first of all, these angles are always going to be the same in here in the cosine and sine, and the r is always in front. So basically, if I want to graph this, there's my r, there's my theta. So I'll call this the real and the imaginary axis. What do? We do our theta first, right? 30 degrees is about maybe right there. And then a distance of 2. Distance of 2 is probably maybe about right here. So that point right there is 2 cosine of 30 degrees plus I sine of 30 degrees. All right, so hopefully you see it's not really that hard. Matter of fact, maybe you wonder why they even do this, but of course sometimes in math you learn to do things before you really know the reason why. Let's do one more, converting a complex number in rectangular coordinates to polar coordinates. And I'm going to do this one because this has got a little bit of a twist to it. And hopefully you'll remember what to do with this, but just to be sure. You know, it never hurts when you're going to convert this. You can always make a quick sketch of this point, because later on you're going to see when we have to calculate the inverse tangent, it's really important to know what your graph is going to look like. So minus 2 minus 5i, so minus 2 on the real axis and minus 5i. So we're down here. Looks like we're sort of in like the third quadrant. Now I want to write this in polar coordinates. Once again, r is going to be the x squared plus the y squared, 4 plus 25 and just so we'll know, just to get an estimate, square root of 29 is like 5.4. Just to have an idea. Now the theta, inverse tangent of y over x, so minus 5 over minus 2. So 5 divided by 2, the negatives cancel out, and now the inverse tangent, 68.2 degrees. Now, if you think about it, here's my angle. Does that look like 68.2 degrees? No, it does not. That's because, once again, we're taking an inverse tangent. My angle is down here in the third quadrant. Inverse tangent does not give me angles in the second or third quadrant. It only gives me angles in the first and fourth. So really, it's really giving me this angle here. So what I can do is I can just add 180 on. In fact, I'll put that little mark there. That's not really my theta. I'll call it theta prime. My real theta is 180 degrees plus 68.2 degrees. I think I can do this one in my head. 248.2 degrees. Remember, this is the whole idea of reference angle. That goes way back. So now I've got r and theta. I know when I write the complex number in polar coordinates, this is my little formula. So r, I'll call it square root of 29, cosine of 248.2 degrees plus sine 248.2 degrees times I. And there you go. Now, how about we go the other way? So here's I'm going to give you a complex number written in polar coordinates. 2 times cosine 30 degrees plus sine 30 degrees I. And now I'm asking, what is this going to be in rectangular coordinates? Well, if you remember, we can just look right here. Here's the equation of a complex number polar coordinates. So it looks like that must be the r, that must be the theta. And then we go back to what I wrote down a few minutes ago. If you're given polar coordinates, r and theta, and you want to find the x and the y, x is r cosine theta, y is r sine theta. So we simply say x, r cosine of 30 degrees, and y is r, which is 2, sine of 30 degrees. Now it doesn't hurt, once again, just to make sure, polar coordinate 30 degrees is right about here, and 2, so we're over here in the first quadrant. So I think x and y should both be like positive numbers. Now actually, I'm going to write down exact values because I know the cosine of 30 degrees. Cosine of 30 degrees is square root of 3 over 2. So 2 times square root of 3 over 2, which is square root of 3. Sine of 30 is 1/2. 2 times 1/2 is 1. So now, written in rectangular coordinates, there's the x part, and the y part's 1 times I. So you probably just write square root of 3 plus I. All right, let me go and stop this video now. And I probably have one more video to go. Now we're going to do some other things. Now that we know how to write these complex numbers with polar coordinates, we're going to do some other kinds of problems and even look at some special formulas that they've come up with.